Hi, today I will present you how to characterize objects by their size, their shape, and their size distribution in perClass Mira. Our dataset is composed of 12 scans of different lentils and bins. The first step is to build a classifier, so we labeled for each scan one or more objects. Once the classifier is built, we can visualize decisions per pixels. We already set whole bins and lentils classes as foreground, so we can see decisions per object. We changed the minimum size of object to 5 pixels in order to include the smallest ones. We define the max fraction of decision for the entire object by setting object mask as all foreground. We can observe that the classifier per object works well. We will see now how we can determine the classifier accuracy using a confusion matrix. In region functionality, we can draw manually a region for each object. Each region is defined by its position and its class. So, in this case, the region has been defined as rice, but we want to set it as black bean. We assign this region as current class for switching. Another alternative for drawing each regions is to import them from an Excel file. First, we export object result to Excel in order to obtain bounding boxes for all of them. In the exported Excel file, we get object index, pixel size, position, object decision, and distribution of foreground pixels per object. We extract needed information such as object index, position, and class. Then we can import them via data, region, and import regions. Each object has been defined by a region which refers to the ground truth. All regions are defined by the color of their class definition. Now we can compare results per object from the classifier and from the truth in the confusion matrix. This confusion matrix represents the true definition per rows and the decisions per columns. In training sets, the rate between label data and the classifier output at the pixel level is computed. In the object panel, we match the region and the decision per object. For the black bean scan, we have 15 black beans, but one of them has been classified as black lentil. That is the reason why we have 14 in the green diagonal. We can compute the matrix for all scans. For example, growths have a true positive rate of almost 87% because 116 have been well classified over 134 objects in the scan. So we have access to number of all objects per class in the right column. Nevertheless, the software detects objects close to each other as connected objects, meaning one object. In this part, we will show how to export particle size distribution and access to real number of objects within a scan. For that, we export, for example, growths and yellow lentils results per object. We keep information such as pixel size, object index, and class. We can process some information such as the median of pixel size for each category. The ratio between number of pixels and the median provides the user information about different irregularities. For a better and quick understanding, we can plot number of objects and pixel size for each samples. In the case of yellow lentils, object index 56 has a ratio of 0. We can compare this result to the scan in perClass Mira and we clearly see that this lentil is broken. We compute the same graph for growths and we observe that a lot of objects are connected because the ratio is larger than 1. In perClass Mira, object ID's visualizations show that a lot of them are connected. In fact, they are counted as one object instead of several objects. Finally, we compute the real number of objects by summing the ratio, and we can compare it to the number of objects. We saw how to characterize the particle size distribution, and now we will show how to extract features about shape of objects. In Feature Extraction panel, we extract information from pixels of objects with centroid inside the region defined previously. We had representation for object shape. Finally, we can export region features to Excel or to XML files if preferred. If the object is matching the region, then the content present will be true. For each object, we get Ferre min and max diameters, shape moments defined by who moments, and some extra information about ratio between area and perimeter. In this graph, we represented the min and max of Ferre diameters for 4 classes. Yellow lentils are not circular because the camera is line scanning. However, each class can be distinguished from one to another. We can also plot the first shape moment and highlight shape anomalies which may be linked to connected objects or broken ones. The ratio between the area and the perimeter highlights that the rice is longer and thicker than the corn. In the last example, we have raw material in one scan, and then we mix them together in several proportions. We built a model for classifying corn, green lentils, and rice, in this case. Then we compute the decisions per pixels. In the output window, perClass Mira provides to the user the fraction of each classes set as foreground and for each scan. It is a quick estimation for the weights of each component within a mixture. Thank you for your attention.